Okay, let's talk about the periodic table. Now, this is really basic patterns. We already know a couple of them, so some of this will be a review, and then some of this will be new, and all of this will be probably the first time you're really assessed on it. Okay, so there's some basic patterns we're going to talk about. We're going to talk about atomic number, which we've heard about, atomic mass, which we already heard about, valence electrons, which we heard about, but I don't know that we necessarily talked about the pattern on the periodic table. Electron shells, same thing. Periods versus groups, families, and types of elements, I don't think we talked about at all. So here's a periodic table, and the first thing you'll notice, well maybe not the first thing, but something you'll notice is they've got these numbers, which we know are atomic numbers. And if you look, it actually goes in order from left to right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. So if we didn't know what this element was, we could predict that, seeing as it's after 46 and before 48, it would have to be 47, which in the early days when all the elements weren't really discovered yet, is actually what they did. They used the patterns that they were figuring out, and they actually were able to predict the properties of various elements before these elements were even discovered and isolated. So that's one thing, is that the periodic table is organized by atomic number. And remember, atomic number is the same thing as the number of protons. Now, the atomic mass generally also increases, but if you notice, there are some exceptions. So it would be wrong to say that the periodic table is organized from low to high atomic mass, but you could say it's generally organized from low to high atomic mass. So sometimes people get lazy and skip the generally, and it's kind of understood that you know there are some exceptions. But if you look, it goes 1.008, 4.003, 6.941, and it just keeps going up. I'll point out two exceptions for you just so you believe me. So if you look at argon and you look at potassium, the weight for argon on average is 39.95 and potassium 39.10. So the mass went down even though the atomic number went up. And then here's another one, nickel and nickel and cobalt. There we go. I couldn't remember it, sorry. So cobalt is 58.93 and nickel's 58.69. So again, we see an example where the atomic mass actually goes down. Let me clear this off for the next part. But let's actually capture what we just said. So atomic mass generally, that generally is important, low to high. Right? So if I asked you, where are the high atomic mass elements, you would definitely say, well, they're going to be down here and over here. Where the low atomic mass will be at the top somewhere, probably. All right, valence electrons. Now, just a quick reminder about definitions. Valence electrons are the electrons on the last shell, and then electron shells, while I'm at it, are where electrons are restricted to reside or live or be in the atom. And these are based on energy, which is something that we talked about a fair amount with our last unit when we're talking about spectroscopes and things like that. Periods versus groups I'll talk about first, then I'll come back because valence electrons and electron shells actually go with periods and groups. So the rows, so going this way, left to right, these are called periods. And then going top to bottom, or bottom to top, I guess, same thing, these are called groups. So a lot, you might be tempted to call them rows and columns, but if you're talking to a chemist, they will take a second to realize what you're saying. They'll understand what you're saying, but you'll look silly. So learn the vocabulary of the science so that you can talk like an academic. So groups are vertical, periods are horizontal. Okay, so how does that connect? Well, the valence electrons are actually the same in all of the groups. So hydrogen, lithium, sodium, potassium, rubidium, etc. all have 1 valence electrons. So here, I'll do it with groups. Groups equal valence electrons. Now, for the transition metals, which we haven't talked about family names, but that's what groups 3 to 12 are called, we're not going to worry about the valence electrons. It gets a little complicated with them. They have something called oxidation states, which we probably won't talk about in this class. Okay, so if you want to find out how many valence electrons carbon has, you can actually just count 1, 2, skip, 3, 4, 5, 6, 7, 8. Although helium's an exception, it only has 2 electrons. We'll see why it's on this group in a minute. Okay, that's supposed to be a 5 right there. So if I asked you how many valence electrons tin has, you'd say, oh, it has 4, which is the same as carbon, actually. These all have the same valence electrons. Okay, periods actually correspond to the electron shells. So let's switch to red. Why not? Equal electron shells. So this first period has 1 electron shell, then 2, 3, 4, 5, 6, 7, which kind of makes sense because remember the first shell can only hold 2 electrons, and look how many atoms are in that first shell, 1, 2, and then once you have 3 electrons, you need a second shell. Likewise, once you have 10 electrons, you need another shell, right? And then what happens to the transition metals and the lanthanide and actinide series, or these rare earth elements? It gets a little complicated. Okay, so we've talked about how electron shells are connected to periods. We've talked about how valence electrons are connected to groups. Now let's talk about families. The fact that valence electrons are the same in groups actually makes elements react similar to each other. Let's write that down, because that's a pretty important point, because we're going to move into bonding and then talk about reacting and all that. So this whole idea that the valence electrons determine how things react is pretty important. Let me get that back on your screen. Okay, and so then basically the idea here is if you have the same number of valence electrons, elements will react similarly. Now it's important to make a difference, a distinction rather. My brother and I look similar. We are not the same. Okay, so elements reacting similar doesn't mean they're the same. So if both of them react with water, producing hydrogen, well, they both might react and produce hydrogen, but maybe one will do it a lot faster or more violently or be slightly different in some other way. But then if you compare it to a complete other group, maybe it won't react with water at all. So similar is not the same as the same or equal. Okay, so families. So there's some that you're actually going to have to memorize. So let's use some highlighting. So this first group in yellow is called the alkali metals. Okay, so ALKILI metals. This second, now notice I left out hydrogen. It's not actually a metal. We'll get back to that after I do the families here. The second group is called the alkaline earth metals. You may have heard of alkaline batteries. Well, these actually use these alkaline earth metals. They're also basic, which is something we'll talk about maybe next semester. Okay, so alkaline earth metals. Students confuse these first two groups a lot because they have very similar names. If you say the first group is alkali earth metals, you're wrong. So make note of the Ne and make note of the earth. All right, this next group is actually a block. Like I said, it's a little different. And these are called the transition metals. So the ones that we're not worrying about valence electrons are transition metals. So I'll never ask you, iron, how many valence electrons does it have? I won't. 2 or 3 is the answer. That's why it's complicated. It doesn't have a simple answer. All right, and then the next group that I want you to actually remember, let's do red, is the halogen group, which is right here. So in red, these are halogens. So fluorine, chlorine, bromine, etc. And then the last group that I really like you to remember, let's do purple is good, is the noble gases. Oops, need to switch to the highlighter. Okay, noble gases right here. Now the noble gases are called noble gases because they don't react with anything. So it's like, oh, I'm noble, you are a peasant, I'm not going to react with you, I guess. These are also called the inert gases. Inert is a vocab word that means they don't react. So there you go. These ones down here are called the lanthanide and actinide series because the first element in the top one is lanthanium, right here. And then the second element is actinium, so lanthanide, actinide. Sometimes these are called the rare earth metals. So that's something that you could remember as well. So let's actually add that. So rare earth metals, here we go. Okay, with our last bit here, I need to clear this off. We're going to talk about different types of elements and the properties that they have. So I'm going to make this a little smaller so that I can type on it as well. So there's 3 different main types of elements. I give you their families, but there's metals, nonmetals, and semimetals, which are often called metalloids. Okay. The metals occupy the majority of the periodic table and are on the left side here. The nonmetals are on the right, so metals in red. Nonmetals, let's do blue. Nonmetals is like this. Selenium is also a nonmetal, like that. So these are all nonmetals, and so is hydrogen actually. So I shouldn't have had that little red spot there, because that would be confusing. Hydrogen's over here because it has 1 valence electron, and it's not a halogen. So it doesn't make sense to put it here. Now helium does not have 8 valence electrons, but it is a noble gas. It behaves like one, so that's why they put it in the noble gas family over here, which I should have said earlier, but I forgot. Okay, so nonmetals is blue. And then in between are semimetals, which have properties that are in between. So they're not really metals, they're not really nonmetals, they're just kind of stuck in between. Okay, so let's talk about some properties. So metals are malleable, which means they can bend. They conduct electricity. They usually have a metallic luster, which just means they're shiny. Nonmetals tend to be brittle, which means they crack. If you ever had peanut brittle, it cracks very easily. It's kind of hard, but it doesn't bend. So if you try to bend it, it'll crack. Glass is brittle. If you try to bend it, it cracks, unless you heat it up, but that's for a different reason. Nonmetals are insulators, which means they do not conduct heat or electricity. So like rubber on the outside of wires is made of nonmetals, because otherwise every time you would touch a wire, you'd be electrocuting yourself, if it had voltage going through it anyway. And they tend to be dull, which doesn't mean boring, it just means they're not shiny. Those are the big ones. Oops, where'd dull go? Here we go. Oh, and I should say semimetals have both properties. So silicon, depending on how you find it, can sometimes be shiny, sometimes be dull. It can sometimes be a conductor, sometimes be an insulator. It just depends on how you work with it. All right, so that's my lecture part. You'll read about this as well, but I actually want you to do these songs. They're kind of fun. So you can YouTube search this one. It actually has captions. I dare you to sing along. And then there's this one, which is kind of a rap as well. So If they get repetitive, you can switch them off, or if you have more time at the end, maybe you can come back. Okay, there you go.